Last time I mentioned how pressure is related to kinetic energy of the ideal gas, that pressure being the pressure it's exerting on its surroundings. And then also temperature is related to the ideal gas, the kinetic energy of the ideal gas. And specifically saying that the temperature is related to the speed of the particles. And actually a temperature is a measurement of the speed of the particles. So let me go through that again. So the pressure that an ideal gas exerting on the walls of whatever container it's in is equal to 2/3 times the number of particles divided by the volume times the kinetic energy, the average kinetic energy, which is expressed in terms of the average of the squares of the velocity of the speeds. Okay? So this is the average kinetic energy for each individual particle, multiplied by the number of particles you have in your ideal gas, divided by the volume, times 2/3, gives you the pressure. Then, rearranging things, plugging in the ideal gas law for here, we end up with the relationship that 1/2 mv squared bar is equal to 3/2 kBT. Where, again, kB here is the Boltzmann constant, T is the temperature of what we're talking about, and V squared, with the average over it, is the average of the squares of the speeds. So you can see that directly related here are the kinetic energy and the temperature, and specifically the speed of each particle and the temperature. Okay, the average speed of each particle in this situation, along with the temperature. Okay, related to it that way. So if I were to rearrange things, I can specifically say how the speed depends on the temperature, and I can do that by factoring that factor of 1/2 out of everything, dividing through on that side by the m, and you end up with V squared is equal to 3 kBT over m. But I want the actual speed, not the average. But you can't just say, taking the square root of this is the actual speed. What this is, it becomes a new quantity, we give it a new name, and that would be the root mean square speed. So the square root of the mean of the square is the root mean square speed of these gas molecules, and that would then be equal to the square root of 3 kBT over m. So the root mean square speed means the square root of the mean, or the average, of the square. So it gives you sort of an average, but not exactly, for the distribution of speeds of each individual particle. So this is what you would use if you wanted to characterize the speed of these particles. You would use the root mean square speed. And so the root mean square speed is equal to the square root of 3 kBT over m, so it depends on the temperature and the mass. So if you increase the temperature for any given particle, you increase its speed. And also, that's why the temperature is a measure of the speed, because they are directly related like this. And if you have different gas molecules all at the same temperature, the ones with lower mass are going to be moving at a higher speed, since mass is down here in the denominator. This is why we don't have hydrogen in our atmosphere, or a very, 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 very small amount of hydrogen in our atmosphere. And it's because the temperature of our atmosphere, the temperature of the ground, because it's being heated by the sun, the speed of the hydrogen molecules, or atoms, depending on if they're separate, but they should be H2 in our atmosphere, they end up being too high of a speed for Earth's gravity to contain it. Earth's escape speed, the escape velocity you need to be moving at to actually escape Earth's gravitational pull, is 11.2 kilometers per second. You can do that, you can get to that with the temperatures we have now with the hydrogen molecule, since it is so light. And so that's why we don't have much hydrogen in our atmosphere, and that's why it's harder for planets to collect lighter particles in its atmospheres. But that's a whole different section on planetary astronomy that I mentioned in class I'm not going to get into now. But this is how temperature is directly related to speed, and therefore kinetic energy, and how that all plays into the pressure. Okay, so in this container of gas, okay, you have particles moving at a certain rate. Okay, and that rate is determined by the temperature of of that ideal gas. And that also then influences how much they impact the wall, because once they have the speed, they have momentum. And then they can transfer momentum with the containers of that is being held in, and that reads as a pressure, as we talked about before. So these things are all related, and that's just getting at the details of what this means to be thinking about the microscopic ideal gas, all the different particles whizzing around there.